You'll have noticed that often we look at shapes of histograms and we can tell quite a bit from the general shape without looking carefully at the horizontal axis, exactly what units things are measured in. We can say roughly where it's going to balance, roughly where the halfway point is, and so on. But if we try to make those observations precise, it's helpful to know what happens when you change units on the horizontal axis. Does the shape really change? In what way does it change, if it does change? And so this is going to be a somewhat technical segment on what happens when you change units, and it will introduce a particular change of units of measurement, which is going to be critical for what you do later. So bear with me while this is a little bit computational. It'll get interesting in section 5. So here we go. What happens when you actually change units? If you convert inches to centimeters, you take your list of inches and you multiply all of the numbers by 2.54. In other words, you're taking your list and you're multiplying it by a constant. When you convert degrees Celsius to degrees Fahrenheit, you're doing two moves. You are first multiplying by a constant and then adding a constant. So you see the typical move is take your list and either times something or plus something. These can be done in any order. Times can also be a divide. Plus can also be a minus, and so you can have your old variable first add something to it, then multiply. Or you have your old variable subtract something from it, divide. These are all similar transformations. The point is that you don't square the variable or multiply it by another variable. If you multiply it at all, it's by a constant. So let's see what happens to distributions when you make moves like this, and we'll start with a simple case where we're simply adding a constant to a simple list. You take a list 1, 2, 2, 3, and you simply add 4 to each entry. You get 5, 6, 6, 7. What happens to the histogram? Well, there's our original one, 1, 2, 2, 3. Once you've added 4, you've got to 5, 6, 6, 7, and what has happened? Exactly. The histogram has slid 4 units to the right. So what does this do to the average? Well, the average was 2. This is visual. That's the balance point. And that has slid 4 units to 6. No surprise there. What has happened to the SD? The SD measures roughly how far off the numbers are from their average. There is no change in that. This histogram didn't get spread out. It didn't get squished in. It has exactly the same spread, the new one, as the old one did. And so nothing happens to the SD. When you add a constant, you do not change the SD. When you multiply by a constant, you will affect both the average and the SD. But when you're just adding, it's a slide and the SD stays the same. That's true for most measures of spread, by the way. So now let's look to see what happens when you multiply by a constant. So it's our same old list, 1, 2, 2, 3. I'm going to multiply by 2. I'll get 2, 4, 4, 6. And while we're being technical, why don't we also deal with the case where we're multiplying by a negative number? That's much less common than multiplying by a positive number. However, it does happen sometimes, and it's worth knowing what happens in that case. So you'd get minus 2, minus 4, minus 4, minus 6. That's our new list. What happens to the histograms? There's 1, 2, 2, 4, and here's 2, 4, 4, 6. And you can see that this histogram has been created by taking the one you started with and stretching out the horizontal axis by a factor of 2. The distance of 1 unit here from 0 to 1 has become a distance of 2 units here from 0 to 2. So also from 1 to 2 here has become from 2 to 4. So the entire horizontal axis has been stretched by a factor of 2. When you multiply by minus 2, you're actually doing 2 multiplications. First you are multiplying by 2 to get to here, and then you're multiplying by minus 1 to get to here, and this last move is a flip about the vertical axis. This bar at 2 became the bar at -2, this bar at 4 became the bar at -4, and this bar at 6 became the bar at -6. And so now certain things are clear from the picture. If you multiply by 2, the histogram gets stretched out by a factor of 2. The new average, well, the histogram was balancing at 2 here, it is now balancing at 4. That's 2 multiplied by your stretch factor. So the new average is the old average times 2. The new SD is the old SD times 2, because all distances on the original scale have become multiplied by 2. When you multiply by a negative number, then certainly your old balance point of 2 has now become a balance point of -4, and so your new average is your old average times -2. The new SD, compare the third histogram to the second, these have exactly the same spread. The new SD is the old SD times 2, not times -2, because it is simply a measure of how far off the numbers are from their center. You remember all that squaring to get rid of signs? We're just interested in the size of the deviations. So the thing to remember is when you are multiplying by a negative constant, then the SD gets multiplied by just the positive version of the constant. Never any negative SD. If you found a negative SD, you are wrong somewhere in your calculation. Please look. So to summarize, the kind of transformation we're looking at is called a linear transformation. You take your original list, you multiply by a constant, you add a constant. This could mean dividing by a constant, this could mean subtracting a constant, and you can do these moves in either order. These transformations are also called affine transformations. You'll see that in your online text. So what happens to the average and the SD when you make a transformation like this? Both operations affect the average. The rule is if you have a linear transformation, then you do to the average what you did to the list. But only one of them affects the SD. This is a slide. The addition simply shifts the histogram along. It does not affect spread. The multiplication either stretches out the horizontal axis if this is a number bigger than 1, or squishes it in if it's a fraction. Either way, it affects the SD. And it affects the SD by how big it is, but its sign is not the issue when you're looking at spread. You're just trying to see what the distance is of the numbers from their center, hence the absolute value of A. And just to make sure that we have got these ideas down and can use them in a calculation, let's do a quick example. If you have a list of daily maximum temperatures measured in degrees Celsius with an average of 20 and an SD of 5, and supposing you in the American system are going to measure all these same temperatures in Fahrenheit, then what will happen to the average and the SD? Well, let's look at the conversion. That is a linear transformation. You take degrees Celsius, multiply by a constant, add a constant. And so you do to the average what you did to the list. You take your 20, multiply by 9/5, add 32, which is what you did to the list, and you get your average when measured in degrees Fahrenheit, 68 degrees Fahrenheit, the typical temperature in Berkeley. Lovely. The SD will not be affected by the shift. It will not be affected by the plus, it will be affected by the times. And so if you calculate the SD, it's just the 9/5 times the original SD of 5, and you get 9 degrees Fahrenheit. And what you're saying is that the bulk of the temperatures are going to be in the range 68 degrees Fahrenheit, plus or minus a few multiples of 9. So maybe 68 degrees plus or minus 18 degrees will pick up quite a big chunk of the data. Chebyshev's inequality says it picks up at least 75%. So this discussion has so far concentrated on physical units of measurement. we're going to deal with slightly abstract change of variable, which turns out to be very useful for viewing data sets. And that is something that you have seen before, though not written out formally. So let's take an example. You have a distribution of heights, average of 67 inches, SD of 3 inches. For quite some time now, we've been doing things like starting at the average and then going a few SDs on either side. So you might start at 67 and go 3 inches on either side, or 6 inches on either side. To formalize this, we are now going to start calling our average, our origin, 0, and the SD as 1 unit of measurement. And there is a transformation that takes us from the inches scale to the scale where the average is the origin and the unit of measurement is SDs, and that is called the standard unit scale. And here's a picture that represents how the transformation works. So there's a lot going on in the picture. We'll take it in bits. The average, 67, becomes 0. 70 is 1 SD above average. That becomes 1. The minute you set down 2 numbers on the scale, everything else is forced to be set down at a particular point. So 64 is 1 SD below average. That must come down to -1. The lower scale here is called the standard unit scale. It is usually denoted by the letter Z. I actually don't know why, but Z is very common for this. And just to make sure that we understand how to move from the original scale to the standard unit scale and from the standard unit scale back up, let's take a look at what standard units are measuring. They are measuring how many SDs above average your number is. So 70 is 1 SD above average, hence 1. 64 is 1 SD below average. That's -1 SDs above average, hence -1. If I go 2 SDs above average, I'll end up at 73 inches. So 73 really should go to 2 here. Let's just take a look at that calculation. So 73 inches, if I'm trying to find out where it is on the standard unit scale, well, first it's 73 inches minus 67 inches away from the average. It's 6 inches above average. Compared to an SD, that's 2 SDs. So the calculation is, if you want to find a value in standard units, you take a height, subtract off the average, divide by the SD. And you can go in reverse. If I look at something that's -half standard units, then it is at -0.5 on this scale. It's going to go somewhere here. It's going to go up to somewhere in the 64 to 67 range. It's -1/2 SDs above average. -1/2 of an SD above average. And that's 65.5, halfway in between 64 and 67, just as you expected it to be. So if you are given standard units and you are trying to find the height, you say it's that many standard deviations above average, and you're done. In general, the transformation looks like this. You have your original units, which I'm going to call x. You have an average, which will translate to 0. The point average plus 1 SD will translate to 1, and everything else is determined accordingly. If you want to find a value in standard units, you take your value, subtract off the average, divide by the SD. If you've got the standard units, then your value is that many standard deviations above average. So you now know how to go back and forth along those scales. A summary: standard units measure how many SDs above average. They are frequently called the Z-score because of the conventional notation Z. We have observed how to go from the original scale to the standard unit scale. And you have also observed, without me telling you, that if z is positive, your original value is above average. It's on the right side of your 0, so on the right side of average. If z is negative, then the original value is below average, less than average. And if z is equal to 0, then your value is equal to the average. And just to tie this in with what we did earlier about linear transformations, it's worth noting that the conversion from the original units to z and from z back to the original units, those conversions are both linear transformations. It's easiest to see here because people are used to seeing the equation of a straight line as variable times a slope plus an intercept. So the z to x transformation is for most people very apparently a linear transformation, but so is the x to z transformation. Here is x, I have subtracted off a constant and divided by a constant that is still linear. And so that transformation, z is a linear transformation of x, equally x is a linear transformation of z. And so what do we know about changes to averages and SDs? Well, if I know the average of x and I want to find the average of z, what do? I do to the average of x what I did to the list itself. So I take the average, I subtract off the average, I've got 0. It doesn't matter what I divide by, I'm still going to get 0. So if you take a list of numbers, the average in standard units is 0 by construction. After you've done that, you haven't really changed the SD because the subtracting off the average is just a shift. But then once you divide by the SD, you're taking your old SD, you're dividing it by itself, you are going to get 1. If you look at any list of numbers that has been converted to standard units, the SD of the list in standard units is 1, again by construction. So what is this telling you? Well, you know that the vast majority of the heights are going to be in the range average plus or minus a few SDs. In terms of the standard unit scale, that is saying the vast majority are going to be in the range 0 plus or minus a few multiples of 1. So maybe 0 plus minus 1, 0 plus minus 2, 0 plus minus 3, and outside that there really isn't a whole lot, because what does Chebyshev tell us? Chebyshev tells us that at least 8/9 of the list in standard units will be in the range 0 plus or minus 3 SDs. So 0 plus or minus 3, so minus 3 to plus 3. If you're looking at a list that has been converted to standard units, you are going to expect to see a big chunk in the range minus 3 to 3. In other words, if you look at a histogram and the horizontal axis has been written in standard units, then the numbers where you're going to see data are mostly going to be in the minus 3 to 3 range, maybe in the minus 4 to 4 range, but really outside that you don't expect to see much at all. So if you look at your histogram and the horizontal axis is in standard units, you should be expecting to see numbers in the minus 3 to 3 range, minus 4 to 4, but not much beyond that.